Hi everyone, welcome to another session of our Friday presentations. Again, my talk is going to be on absolute zero, reinforced self-play reasoning with zero data. My name is Griffin Higgins, it's May 16th, so let's jump into this. A little bit about me, I'm a PhD student here at UNB, and I'm also a cybersecurity software developer at CIC. I also love nerdy things. A little fun thing about myself this summer is that I got a longboard. So if you ever see me with a little bit of a limp, I'm just kind of learning to longboard, so my right leg is killing me. And yes, that is a Python on the skateboard, so no relation to the programming language, but I did pick it because of that. So for the agenda, I'm just going to talk about this paper. It's really cool. We're going to go through all these different sections, and then I'm going to give some of my critiques, my questions for the paper, and then I'd love to hear some of your questions about the paper as well. So let's just start with a hypothetical. Let's just say that someday I graduate, and let's just say that someday you come to take Python 101 with me in a class. If I'm the professor, I might want to teach you programming languages and then eventually evaluate how well you might be doing on this. And I can do this in a couple ways. The first way is that I might construct a program triplet. And we might think of this as the input, which is just hello world, the function itself, which is just the identity function in this case, as well as the output, which is also hello world. But we can start to test our students in a variety of ways. One way we can test them is deductively, right? So I give you the input, I give you the program, you tell me the output. We're going from general to specific. I might also ask you an inductive kind of reasoning question, where we're going from specific to general. So I give you the input, I give you the output, you give me the program. And again, there might be multiple ways to define this program, so it's not waterproof, airtight, but we can still make something that conforms to this. We can also consider the abductive case, where again, we're just taking one of these things away, and I give you the program, and I tell you the output, but I don't tell you the input, and you have to kind of guess. And again, this is the best explanation for a given observation. So it's not absolutely watertight. There might be multiple different valid inputs, but as long as you give me one, that might work out. So you might be saying, Griffin, in this hypothetical class, so what? Why do I care? What does this mean for me? It would be good because I can evaluate you on this, but it's also interesting because what happens if instead of me trying to give you these questions, over time as you accumulated knowledge of how to program, you actually could give yourself examples to maybe learn more and more and more, right? So what if we actually asked an LLM to generate us these kind of triples with the inputs and the programs and the outputs? What would happen if we did this? Well, we can kind of see in the last case where we're going to talk about absolute zero, we moved from the supervised case where people literally sit down and they handcraft these X's and Y's that machine learning algorithms need to learn. But later on, we might actually, instead of crafting them ourselves, we might actually use reinforcement learning and say, this is the generic thing I want you to do, go ahead and do it, but it's verifiable at the end of the day. But the thing we're going to be talking about today is what happens when there's no humans in this loop. What happens when large language models essentially start training themselves. Another question we might ask is, okay, I buy this, I've seen lots of input and output from ChatGPT, but how do we know if it's actually going to make a valid triple? Because it can construct lots of crazy things, and how do we know if it's going to be valid or not? And this is a really good question because it introduces some level of ground truth. And the way we're going to provide this ground truth or this source of truth is through the Python interpreter itself. So after we ask a large language model, hey, generate me this triple, what we're going to do is we're going to pass it through the Python interpreter, and we're going to validate the integrity that the program works. We're just going to run it. We're going to validate the safety of it. We're going to make sure that it's not going to just ransomware off our whole computer. We're also going to ensure that this is a deterministic program so that the LLM might actually be able to reason about it in a non-random or stochastic way. So, okay, I would say I buy this. This seems like a good idea. But another question we might have is, okay, so how does this actually learn? Like, it makes sense, but how does it learn? So we might actually move into the system of how this absolute zero reasoner, which is what the authors propose, is going to work. And we've already covered this little section here in red, where we consider the adductive, the deductive, and inductive cases for creating reasoning scenarios that we can verify down below. But what about the rest of all of this? How are we going to solve this issue and make triples and solve the triples and figure out if we're actually learning anything? What if it's too hard, and what if it's too easy, and all these kinds of questions. So we're actually going to decompose this into the following kind of state transition diagram, where we're going to have two roles. One of them is going to be the proposer, the other one is going to be the solver. And if you're the proposer, you're first going to propose one of these triples in step 2, and then we're going to pass it through the environment, make sure that everything checks out, just like we just talked about, and then we're actually going to give it to the solver to solve afterwards. And then we're going to move through a similar thing, where we again validate it through the environment, and then solve it and see how we did. You might also ask, what is this R propose and what is this R solve thing? How does it work? Well, in the case where we're proposing examples, after we solve them, we'll know kind of how we did. And if it turns out that the LLM isn't capable of solving any of its own examples, we're probably going to start excluding those examples and say, hey, try something easier. In the other case where it can't solve all of its examples, I forget what I just said. The inverse case, we're just going to make sure that it's not that. So anywhere in the range from 0 to 1 that is valid, it means that we're actually going to be learning something. And on the other case, for our solve, we're just going to make sure that the predicted input is equal to the actual input, that we have validated but not actually crafted ourselves as humans. So, okay, what else is here? There's also this kind of scoring mechanism, so that as we're generating proposed triplets and solving the proposed triplets, we're going to consider, like, if the response is wrong, but it's well formatted, that's also an issue. Like if we ask for an array back and it gives us a string back or something, but maybe the array is good, I don't know. But if it's mostly all the way there, then we might penalize it a little bit. But if it actually has like really wrong formatting answers, then we might penalize it a lot. And we can also apply this to both the proposer and the solver. So, okay, where might we go after this? Well, we might want to actually evaluate this in terms of metrics. So here we're going to consider 6 different averages, one for the inductive case, one for the deductive case, one for the abductive case, and then all of those for both the proposer and the solver as they start to actually learn. So, okay, and this also is called task relative reinforcement plus plus is what the authors term this. I believe it builds on something else that's existing. In terms of the experimental setup, we covered kind of the general overview now, so let's move into like what they actually did for real. They divide their data sets, they consider quite a few of them, into in-distribution data sets for the benchmarks, i.e. like the things that other people have actually run before, as well as like out-of-distribution data sets, so maybe things that other researchers haven't considered, but that they're just going to use. And they specifically focus on coding and math, so they have all these different data sets for those 2 specific things. And we'll get to what some of the implications of this might be in a moment. They also consider the following models, so they use Quen 2.5 to 7 billion parameters as what they call their absolute zero reasoner base. And then they consider the Quen 2.5 coder to make their own absolute zero reasoner coder version. So right now it's the same model, but nothing's been trained, but after the fact, then it would be their model. So okay, what about some baselines? For the coding kind of models, they use ACE Coder, which is a model, I guess, that's meant just for code, as well as Code R1, and there's different kind of variants in there. I think some of them might be instruct, some of them might be for code, some of them might do different things, but there's some variants. As well as math-specific models. I'm not gonna list them all out, but they're there, as well as some general ones like Llama 3 and SimpleRL Zoo. So, okay, after we consider the benchmark, the data sets, the models, baselines, we might also take a quick peek at the hyperparameters. I'm not going to stay on this too long, but if anyone has any questions about this after, I'm more than willing to take a look at it. But this is probably the most important thing, is just the results. So I'm not a big fan of tables, but this is probably the most concise way to express this. Everything we see in blue is coding models that have been trained specifically on curated code data on those code data sets. So they should do very, very well. Everything you see in red is the same thing, but for math. So again, these models should do very, very well. And then down below, in green is the absolute zero reasoner model. And we start to see some very interesting things. We start to see that specifically here, anything in black that you see is kind of the best score for that category. So we can start to see that. One last thing, I guess, is that the data column is here. So that's the number of examples that people have actually handcrafted and curated for these things to learn. And we can see basically one of the most important results is the absolute zero reasoner down below. It has no curated examples. It's totally just being derived from the model itself. So this is pretty interesting because if we look at the coding average, it gets the soda. It doesn't get soda for math, but just on average, it gets soda. So that's pretty remarkable. And the only case where it doesn't get soda on the math average, it's competing against a model that has almost 500,000 handcrafted examples. So in this case, that's pretty remarkable because it's like saying if I have to spend $1 trillion to get a model to get 99% accuracy versus if I have to spend a dollar to get a model with 95% accuracy, like the benchmarks or the accuracies might not be there, but the cost to get there is quite extreme, especially when we start to think about how this might not actually scale, right? Like we might not actually have 1 billion math examples there sitting in some database, but maybe the large language models can actually start to generate these examples and learn from them over time. So yeah, happy to take some more questions on this after. One last thing is, we'll talk about briefly after, is that the two green benchmarks up top for the baseline models, we can see that the math model and the coding model, they kind of are inversely flipped on the math, but then later they flip again. So we'll talk about that some more, but this is just the generic results, which are pretty awesome. In terms of the research questions they ask, they say, how does absolute zero reasoner compare to the zero model or the zero setting models trained with Huron expert data? It claims to achieve state of the art, so that's not bad. And then for research question 2, how do initializing from different base model variants, i.e. the base coder, affect the performance? This is the thing I was just talking about. So very simply put, if we have a base model and we test it on math, it gets 27.5% accuracy. And if we take a coding model, it gets 23.9% accuracy. After we train it with the absolute zero reasoner, the coding model does better on math than the base model did before. So that's kind of interesting. That's something that's not trained to do math, it's trained to do code, is doing better on math. That's pretty cool, and the authors suggest that this might be it actually learning to generalize across the logic. When we think about how it learns abductively, inductively, and deductively, it's going to learn those generalization skills that might also apply to math. So that's pretty cool. Research question 3 was, how does varying the model size affect the absolute zero reasoners in distribution and distribution capabilities? The long story short is just that bigger models have better gains, right? So if you have a 14 billion parameter model, you're going to see it have a plus 13% average accuracy increase over maybe a 3 billion model that might have 5.7% accuracy increase. And then any interesting observations by changing the model class. So instead of using Quen 2.5, they substituted Llama 3.1 in just to kind of prove that it's not just something weird happening with Quen. And again, it also improved at 3.2. They didn't test too many more models with Llama 3, just because, as you might imagine, this gets expensive to do this giant grid search with these things over time. So at least they did that. A couple more interesting research questions. They wanted to know any interesting behaviors or patterns observed during the AZR training. There were distinct reasoning for different types of tasks. So that makes sense, right? Like if I give you a program and I only give you the output of the program, in order to think about what the input might have been, that's very different than solving the output kind of deductively, right? You might have a very different chain of thought. And speaking on chain of thought, they also observe intermediate planning during the code response. So as it's learning to come up with these examples and making the functions in the code, it's actually starting to interleave the comments. And one of the things the authors hypothesize about that is it's a medium for the solver to communicate with the proposer by saying like, hey, this is what might be going on with this problem or not. And then they also observed a token length increase depends on the task type. So especially for abductive tasks, where it's just trying lots of things and inputs that might actually generate a correct output, versus like if you're just looking at it deductively, you might be like, yep, this is how the program works, here's the solution, right? And then I guess moving into some ablation metrics, basically if they start to remove the model's ability to learn deductive tasks or inductive tasks or abductive tasks, what happens? And they observe kind of drops in all this accuracy. So one of the biggest findings, I guess, is just that all of these types of reasoning and learning are needed in order for it to improve. And then one of the last research questions was, how much do the design of the proposer contribute to the overall performance? And again, it was pretty significant. And I think here, if I recall, they were just trying to limit some of the capabilities where they might only have the solver kind of update in that vein. So, okay, a little bit more on the discussion. They talk about this idea of using other simulators, because if we think about the Python interpreter as just being a black box of truth, right? But we might be able to substitute any kind of black box of truth in there. We could use Java or real world or World Wide Web or other math languages, things like this. And then they also have some safety concerns. So in one of the chains of thought where it's thinking, it says design an absolutely ludicrous and convoluted Python function that is extremely difficult to deduce the output from the input, designed to keep machine learning models such as whatever, and your peers puzzling. And then right after that, it says, the aim is to outsmart all these groups of intelligent machines and less intelligent humans. This is for the brains behind the future. So, you know, maybe we don't just let this thing go off and learn anything by itself, but just something that we should be aware of. Yeah, so now that's kind of the entire paper, very quick walkthrough. But what are some of my kind of critiques, I guess, if I were a reviewer of this paper? One thing I would say is, like, why aren't other programming languages considered? We just consider Python. Why not use Java? Not a huge fan of Java, but it is strongly typed, right? So maybe that would give the model more ability to define things and learn stuff, who knows? I would also be very interested to know if it's using like regular expressions of any sort, because that's almost like a sub-language if we think about it within Python. It's not really a language, but it'd still be interesting to see. And then I said that they should explicitly state why Quen is used as the base model. All this LLM stuff moves so fast. I've been doing a lot of graph stuff lately, and I just kind of lost track of what the state-of-the-art model was. So that might be good to include, even if it's trivial. Another question I had was, why isn't, you know, for research question 4, where they say bigger models have bigger gains, why don't you just go all in and try this with DeepSeek R1 with a giant model, and maybe we get AGI? I don't know. And then I guess other things would be the inclusion of the numbers and the parameters table would be good. You know, if something was a 3 billion model versus a 7 billion parameter model. Couple typos, but that's not anything to cry about. Some other critiques were just, they talk about how the model should be restricted from certain imports and modules in terms of safety. So maybe don't give it access to the OS module to delete a bunch of files or move things around. But they also talk about how they're only considering these things to be banned, specifically the Pebble and bcrypt modules. I don't think they're standard library modules, so I guess one of my questions would be, is the model allowed to access non-standard modules like pip install it or something? I don't think so. Python version number should be included. And then I'm not sure how much I buy this absolute zero claim. The base model is not exactly tabula rasa, which is just a very fancy way of saying a blank slate. If we think about it, this model has been trained with data from the real world, and essentially I view this as like, maybe we haven't given it all the data it needs, but all the data is there. It can learn from the existing data, so it just kind of pushes it out a little bit with what it has. So it's not exactly starting from nothing. It has something to work with, but it's still very cool what they do nonetheless. So those are my critiques. Some of my questions would be, could we observe general patterns in the training data for various absolute zero reasoner models to create an optimal curriculum, if you will, training data for future models. So we can see maybe if the problems are too hard to start off, maybe we won't include that in our initial curriculum training data, and instead substitute it with zeros. Maybe we can perfect this somehow so that it can just learn as fast as it can. And something else, I guess, would ensembling have any benefit? I forget what I was thinking when I wrote this, but I guess that's another question I would have. And could we get the model to write its own programming language, right? We could ask it to say, like, hey, you don't have to think and write all these functions in Python. Maybe there's a way better, maybe there's a way better programming language for you to actually do all of this in and think on your own terms, if you will. And then the last question I would have is, what happens if you consider a state-of-the-art model trained on curated data as the base model? So what if we don't start with a base model? What if we start with this model that's like really good at math and it's been trained with half a million examples? Would it also extend it further, or is there kind of like this ceiling to how far it can go? Those were kind of my critiques and questions. And yeah, here's the paper reference. It was published like last week, so it's pretty hot off the press. It also comes with a GitHub, so that's awesome. And the interaction is pretty staggering. It has like almost 1,000 likes over a week. I know that's not like citations, but I think that is a really interesting indicator of engagement with real people using this in the real world. So with that, I would like to say thank you so much for listening, and I'll take any questions, and I hope you like learning about AZR.
Yeah, thank you very much.